Okay, so let's begin. So let's welcome the second talk this morning, talk by Miosz PANFIL from University of Warsaw, and he's going to tell us about knot theory, lattice paths, and partition functions.
Good morning. Thank you very much for the introduction, and thanks to the organizers for putting together this very nice event. So indeed, I will talk about knot theory, lattice paths, and partition functions. So this is somehow a part of a research that I was involved, and it was happening over some years with different collaborators. But today I would like to talk really probably mostly about our first work, which touches on the, on the subjects listed in the title. Mainly because I think there's some open question which we couldn't kind of answer, so I thought that maybe communicating the question with others might help with resolving it. So let me start with a bit maybe general outlook. So essentially, when doing statistical physics, we are asked to compute partition function. But in many circumstances, this partition function has a certain structure, which can be maybe summarized in the following three observations: that usually there are some degeneracies. Often, if we think at least about maybe like 2D statistical physics models, the energy can be quantized in the sense that going over different configurations, you change the energy by some definite number. And usually the allowed energies are bounded from below. So with these three things, we can think about the partition function as essentially a combinatorial problem, so where these numbers Cn, they count degeneracies. But now we don't have to think about them as degeneracies. We can think about them as some answers to some combinatorial problem in which we are counting some things. Okay? Physically, we are counting things. We are counting configurations of the same energy. But there might be different picture behind those numbers, and my talk essentially will be about finding this different picture. So in order somehow to find this different picture, we will need a certain tool, and this tool are quivers and related motivic generating functions or series. So quiver is a connected graph, essentially. So we'll think about either graph or related adjacency metrics. And to each or to such a metric, we can assign a series of this form. So that's a quite complicated object, but so it's a function of m variables. So m stands for the for the size of the matrix here. It's an infinite series, then in m indices, and the function is a kind of a power series with a prefactor which contains information about the quiver. So quiver enters here, and then there is a bunch of QPOC hammer symbols, so essentially kind of factorials. Okay, so for us. I mean, these functions appear in certain contexts in mathematics. This is quite maybe deep and involved, so I'm not going to talk too much about that. So for us, this motivic generating series is just a way of defining a family of functions, and these functions are coded by the quiver, or essentially by this adjacency matrix. So given the matrix, you have a function, and we will use this function to relate problems from of computing partition function to a problem of some combinatorial nature. So as I said, these functions actually have some rich structures. So for example, it's completely not obvious that this kind of quiver series, that this kind of power series can be represented in this product form, with this omegas here being integers. Okay, so this takes some mathematics to prove. There's also a kind of a physicist proof of that, because it turned out that if you do, you can find such objects in at least in some variants of string theory, and then those numbers from the physical point of view, it's clear that they are integers. But there's also a mathematical way of proving this, by going.
Do they appear in the theory of three-dimensional manifolds?
Also, yes.
Originally.
Yeah. But this, from physicists' point of view, they can be related to some BPS counting.
Absolutely.
Yeah, and then we know that there are integers.
It's such a geometric paper,
Yeah. Okay. So essentially, now, as I said, there's the talk kind of belongs to a wider line of research. So in this line of research, the quivers play the central role. So we're kind of using them as a vehicle that with which we were connecting different subjects. So originally, at least for us, they appeared from the string theory and then the kind of true knot theory that I'll be talking in a second. They were realized that certain objects can be described by quivers. Then we found different applications of those to the lattice paths that I'll be talking mostly. Another way of thinking about quivers, and by quivers I really mean this the series assigned to the quiver, is that there are some generalization of Q hypergeometric functions, so they also obey certain differential equations that generalize the differential equations of Q hypergeometric functions. A very interesting part is that kind of relation between quivers and topological recursion. So if there's time, I will mention this at the end of the talk. But today I will mainly talk about kind of this edge of of the picture. Right. So let's say a few words about the knot theory. So essentially, well, this is a knot. Now for us, our mathematicians, knot is a loop, so it has to be closed. And the main question about main interest in the knot theory is in classification of knots, or in kind of being able to distinguish whether two things are the same or not, or two knots are the same or not. So, for example, we would like to ultimately answer this kind of questions, right? Are these two knots the same or not? So the way to do this is to assign some mathematical objects to knot. So we kind of view there is a map between a knot and an object, and then if this map has nice features in the sense that if the knots are the same, then the value of the map are different. If the knots are different, then the value of the map is different. Then we can use this map to distinguish different knots. So this is the basic idea behind the topological invariants. So a simple topological invariant is a number of crossing. So this already gives you some idea. So of course, if there is no crossing, this is different than a knot in which you have some number of crossings. So as you can see, if we classify knots by a number of crossings, there's one with 0 crossing, one with 3 crossing, one with 4 crossing, already 2 with 5 crossing, and 3 with 6 crossing, and 7 with 7 crossing, and so on. So it kind of quickly explodes, and there are hundreds of knots with 10 crossings and thousands of knots with 15 crossing, and so on. So minimal number of crossings provides certain classification of knots, but it's not enough, because it doesn't allow to distinguish between these two knots, okay, because they have the same number of crossings. So we need something better. So what people are trying to do is to find better and better topological invariants. So recent kind of highlight in this field is that now it was proven that now we have a topological invariant with 100% guarantee distinguishes one knot from all the other knots. Okay. So this can be proven, but we don't have means of being sure that you compute some invariant for this trefoil knot, and we are not sure if there doesn't exist another knot somewhere far in the series which might have the same topological invariant. So I'll be a bit more specific of what topological invariants I'm talking in a second. So now to connect with physics, so we would like to build topological invariants of knots from essentially statistical physics or 2D statistical models. So the idea is quite simple. You take a diagram of a knot like this, and you think about this as a 2D lattice, in which, well, every crossing is a vertex of the lattice, and the thing that we need to distinguish is whether the crossing is, it can go one or the other way. So we have vertices of two types. Now, in order for this, if you want to build an invariant, essentially it means that on the left side we are allowed to deform the knot as long as we don't, cut or join pieces, which means that we can deform this lattice of the 2D statistical model. And it was understood quite some time ago what are kind of basic building blocks of deformations from which you can build any deformation. So there are two moves which are quite simple. You can make a loop, but this is the same as not a loop, right? You can have two chords running parallel to each other, but with not. So both crossings beside different signs, they really mean that this one is always above the other one. So I can remove it. So of course it doesn't change the knot, but it does change the lattice. Okay. So these two moves are kind of natural from the point of view of knot theory, and there is a third move which is natural from the point of view of integrability. Oh, sorry. Something went wrong with the slides, but the third move is essentially the Young-Baxter equation. So whenever we have a crossing like this, and this one is above those two, we can bring it on the other side of that crossing. Okay. So it turns out that due to Rademeister, with this three types of move, they kind of exhaust the possibilities, and you can build any deformation from them. So now the kind of question or the task before us is to build a statistical model which partition function will be invariant under deformation of lattice given by these three types of moves. Okay. So because the kind of most complicated move is the Young-Baxter equation, we kind of know where to start, because it's enough to start with integrable statistical model to have this move implemented automatically. So all we need to do is to implement the other two moves. And the solution is quite simple, because you take just a kind of integrable vertex model, and you have to kind of add an information about the angles, essentially. So right. So the story is the following, right? We want to construct the 2D statistical model, which partition function is invariant under deformation of the lattice, and the allowed deformation of the lattice follow from the fact that we want to describe a knot invariant. And the key deformation is the Young-Baxter equation. So if we start with integrable 2D lattice model, we're kind of halfway through. So then we have to kind of enhance this integrable lattice model, but by essentially allowing the weights of different configurations to depend on the angle of the lines, because this is essentially what you need to describe this kind of things or these separations. Okay. So yeah, weights from integrability plus enhancements, and we can do this it can be easily done for any representation of UQSLN. And so, for example, just to kind of display something, for fundamental representation, the weights are the following, and then this enhancement adds a theta-dependent factor in front of those weights, and the factor here depends on the values of the spins at the given vertex. And there is one more weight that you assign simply to a fact that the line turns, right? So to this situation. Okay. So we need this in order to be able to describe these two configurations as the same. Okay. So then, yeah, so we have a knot. We built from integrability. We built a statistical model, and then we choose n. We choose some irreducible representation, and we have a partition function, which is a knot invariant. So in this way, if we choose really UQ-SLN, what we get as a partition function are the kind of well-known Humphrey PT knot invariants. So these are knot invariants that were discovered from just without this construction, just say purely mathematically in the 80s. And they depend on 3 variables, so the choice of n, q, and the representation. And actually, it's a mathematical theorem that those invariants are polynomials in variables q and variable a, which is q to power n. Okay, so this is a kind of non-trivial step from here to there, right? That these are polynomials. And for the trefoil, they take the following form, so they're quite complicated already for the simplest non-trivial knot. Okay. So computing them is really hard. So also for practical reasons, okay, we can construct, of course, this 2D statistical model. It's a simple model, right? It has 3 vertices. There is no problem with evaluating partition function, summing over all configurations. But then you have to do this for various representations, and to in the end to come up with a closed formula requires some work, and it's not obvious. But at least in principle, the integrability provides us with means to explore those objects. Yeah, symmetric representation. Yeah, yeah. No. It's just I don't think. Yeah, I think it just comes from the geometry of the lattice, from the winding that you have to do if you want to close the. Right. So now it turns out that all this information in this function can be repackaged in the form of this quiver generating series. So there is a quiver which takes this form, and it corresponds to this trefoil knot, which packages all this information in terms of this quiver generating series. So the correspondence is the following. So you have to take this quiver function. The quiver is of size 3 by 3, so you have 3 variables, and then the quiver the quiver matrix is of this form, so you plug it here, and you have to do some specialization of the variables to move from the kind of knot invariance variables to quiver variables, to these 3 axes from the quiver variables, and in this way we obtain an object which is essentially a generating function for these Humphrey polynomials in any representation, in any symmetric representation. Okay, so this is a very efficient way of encoding all this information. So instead of looking at these polynomials at each r, we have now all this information encoded by saying, well, you have to choose quiver of this size and make this specialization of variables. So this is a super economic way of capturing all Humphrey polynomials, at least for symmetric representations. So this is this is a kind of a first appearance of how this quiver generating series can be useful in repackaging information into something maybe better to digest. Yes. It works, but it's believed to work. But so for example, what we know so far is this knot quivers correspondence, which is to say that to a Humphrey polynomial of a given knot, there is a corresponding quiver, and then this relation of such form has been proven for some families of knots. but you have to be you have to choose specific family of nodes, and then you know what are the Humphrey polynomials, and then you can prove it. But of course, in principle, we would like to kind of invert the logic and say that, well, maybe we can guess a quiver for a given node and then get the invariance. But this is, yeah, I don't think we are there yet with the understanding of this. Anyway, so as I said, one way of thinking about this is that now these quivers allow us to repackage all the information in this so-called colored Humphrey, colored because there are different representations, Humphrey polynomials into something more economic. Okay, so that's kind of this part. So now let me move to the lattice paths. So lattice paths, this is the following kind of combinatorial problem. So we look at the grid, we pick a line, y equals x, y equals 2 over 3x, y equals p over q x, or p over rx, where p and r are coprime integers. And we ask a question, in how many ways by going to the right and up, you can reach the points where this line crosses the grid. Okay, so for example, there is one way to get to that point, but there are two ways to get to that point. Okay, and the rules of the game is you cannot go beyond this one and you cannot cross this line. So if you start, so for example here, to give an example, we have two ways to get to this point, this one, and then more ways to get to the other points. So you can do the counting and start filling this with numbers. So these numbers are like 1, 1, 2, 5, 15, which if someone might spot Catalan numbers here. There are for 2 over 3, the numbers are 1, 2, 23, 377, and the task is to understand how these numbers appear, okay, or kind of find a way of computing them without doing the stupid counting. So one way to kind of reformulate the problem is to, again, not think about the individual numbers, which are the CIs, but think about the generating series for them. And this problem was actually solved in more than 50 years ago by Beasley, who has shown or proven that this generating series takes this form, where P and R parameterize the line. Okay, so for any choice of P and R coprime, we have generating series from which we can get the numbers. So this problem is solved. Okay. Amazingly, this problem was solved in an article, I think with the longest ever title. This was a derivation of a new formula for the number of minimal lattice paths, and very descriptive. I don't think we use, we don't use such titles anymore. But okay, it's solved. Now this problem has a nice generalization because we can refine our counting. So far we were, every path that reached that point were treated equally. We can start to distinguish between them. And one way of distinguishing between them is to thinking what kind of area the path covers, maybe between this line and the path itself, or equivalently between this, the horizontal path, the horizontal line and the path. Okay, so we can refine the generating series by including the information about the area that the path covers, and we package this information by saying that there is some parameter q to the area of the path, or between the path and the line. And of course, when q goes to 1, we go back to the original problem. So we would like to think about q as a kind of quantum deformation, and this is a classical limit. There's an algebraic approach. So the fact that we like to think about this q as some kind of quantum deformation makes sense, at least from this perspective, that there was an algebraic approach developed by Duchon, which is based on non-commutative grammars, or kind of non-commutative languages. So you can, well, actually, I can make a drawing So this is very simple, because if you think about we can encode a path by saying, that we go to the right some number of steps. We can encode a path by saying that we go to the right some number of steps, then we go up, right, etc., etc. So if you assign letters to that, so A is right, B is up, then certain path like this one would be A, if I'm not mistaken, 1, 2, 5 A's, B, A, B, okay? And then if I exchange B and A, I will jump a bit earlier. So I will decrease the area. So I can exchanging B and A gives something like Q2 minus 1 AB. Okay, and that's how non-commutativity of this enters. So we can think about A and B as some objects that do not commute. And then Duchon has shown how to kind of enumerate all the paths, including this, the area that they cover. And then kind of step by step, I mean for every choice of the line, one can write a set of equations that allow to compute this generating series. But unlike the Beasley result, there's really no kind of closed formula like that would work for any P and R. One has to kind of go case by case in that case, that situation. Okay, so now here comes the kind of the highlight of what I'm going to of what I'm saying. Now it turns out that there is that this lattice path counting problem is related to knot invariance for a certain class of knots. So there are knots that are called torus knots, which are this is an example of a torus knot, but essentially they're constructed by kind of, you take a rope, you go around number of times, you go P times around, but in the same time you go R times kind of winding around. Okay, so we have two parameters P and R. So those are the same parameters that appear in the lattice path problems. So to every knot, torus knot PR, there is a lattice path counting problem, and the two are related in the following way. So if you take this Humphrey, well, here it's stated for quivers. Well, maybe I should go this way. So if I have this torus knot, I can write this generating series for all the representations. So I want this object. So this object is represented by a quiver. And now I can take the same quiver and study this ratio. And this will give me the generating series for this Q-weighted lattice paths. Okay. So this is experimental mathematics. So it has not been proven. We've seen examples of that for a number of torus knots. The main obstacle is that no one knows what are the Humphrey polynomial for all the torus knots. So we cannot, there's nothing to play with. But for the cases that we could play with, we have checked and this works. So we kind of use this in a constructive way, in the sense knowing, starting with lattice path, we could reconstruct the quiver, assuming this relation. And then from the quiver, we could get the knot polynomials. So we've checked that this worked. And in the process, we also found the quiver for the torus knots that were not known before. Okay? And that this is not a trivial statement. I will show you how the quiver for a torus knot 3/8 looks like. Okay, so this is the matrix essentially that you have to find. Okay, and by saying experimental mathematics, I really mean experimental. So there was a point in my life when I was sitting and deciding whether there should be 15 here or not. Okay, I'm a bit exaggerating, but not too much. Okay, okay. So these are the Yeah. How much time do I have? 5 minutes. Okay. Right. So maybe let me just iterate it again. So essentially, this is so the main finding, at least of our initial work, was that there is this relation. So to every torus node, there is the lattice path counting problem. So and then each invariant of the invariants of the torus nodes are computed from kind of statistical physics picture. So in that sense, this relates computing partition function to solving certain combinatorial problem. Now, before maybe going here, I will do this. So, so I think there is. So I mentioned that there is a kind of open question which I would be kind of very happy exploring further and answering. Like so, we have a relation between partition functions of integrable models and lattice path counting problem. And this relation relies on the fact that those are integrable, but it kind of goes through knot theory, those quivers, etc. It would be, I think, very nice to cut short this relation, and I believe there should be some direct relation between lattice paths and representation theory of UQSLN. I don't know what it is and how to find it, so if anyone has some idea, it would be great. Because also from my point of view, I mean, from this point of view, like lattice paths are very simple, right? I mean, you just draw some pictures and count paths and include area, and in the same time, this should be related to quantum groups, which is somehow a bit deeper subject. So it would be nice to have this direct relation between the two. Now, before the end, I just want to mention one other result very quickly. Well, maybe I can just start here. So essentially, it can be shown that this quiver generating series, when reduced to a single variable, so in general it's a series of many variables, but we can choose them to be equal. So if we do this reduction, one can prove that there is an operator annihilating it. Okay, so this kind of relation is fulfilled. So these operators x and y have a simple representation. They follow the Weyl algebra, so x on polynomial of x multiplies and y does kind of a derivative, q derivative. Okay, so it can be well, not proven, but it's been seen in many examples that such an operator exists for a given quiver. So it depends on the quiver. And in the same time, we can think about Q as being kind of e to power h. So this then this quiver can be shown that this quiver generating series have the following asymptotic expansion in h bar, which should remind you of the like a WKB expansion in quantum mechanics. Now one can kind of play the following game. So assuming that this operator, this operator is a polynomial in x and y, okay, in these operators x and y. But we can take a classical limit of q going to 0 in which x and y just become variable. So this gives us this kind of classical so-called a polynomial or spectral function sometimes called. Now the game is the following. If I know this a, I know S0 and S-1 of this asymptotic expansion. Can I recover all the other pieces? So this is really what you kind of do with WKB expansion, just reformulated in a different language. And it turns out that it is possible to compute S1, S2, and in the end kind of recover the whole quantum operator annihilating this quiver partition function. And what we found somehow miraculously is that the procedure is the topological recursion, which I don't have now time to introduce, but if you heard about it, you know what it is. But in the outlook, it's kind of interesting that the topological recursion, which was constructed for a completely different reason, to study matrix models, provides a quantization scheme that applies to this quiver generating series. So we have verified it for a number of examples that this is the case. So it seems that like the topological recursion captures something universal about how to quantize system. And by quantize, I mean really something, well, of this form. Okay. So with this, I can go to the thank you. So thank you.
Any questions to the speaker? Not questions?
Can you comment a little bit more on the topological recurrence?
Yes, I mean, so, okay, I mean, this would require writing some formulas, but the idea is that knowing these three objects, there is a procedure with which you compute the other, and topological recursion provides this procedure.
So the wave function, is it?
Yes, so this plays the role of the wave function, so there's like this is like a Schrödinger equation. In the variable q or e to h, it has the standard asymptotic expansion. So the methods WKB type are applicable. And then...
So of course you need the ODE, so the Schrödinger equation.
Yes.
This is a for you, no?
Yes, so this is...
That means that they are quantized.
Yes, so this is my Hamiltonian. And this is my wave function.
Can I interpret as an ordinary differential equation? It's really a Schrödinger equation, or there is something subtle?
I mean, it's kind of discrete in the sense that this y operator does the q difference. It's not a derivative.
So it's a finite difference.
Finite difference equation, yes. Yeah.
Then the expansion is a little bit trickier, no? The WKB is
Yeah, that's why but there's the kind of topological recursion that replaces that, and then we can do it systematically. But the topological recursion itself is quite difficult, so it can be done only in practice for this functions A of a special form, because if the function A is too complicated algebraically, it's impossible to run the topological recursion. But there are some cases in which it can be done, and then it turned out that
like hyperelliptic.
no, it has to be genus 0. That's in practice the A to be implementable. Otherwise,
And so other nodes to which it is effectively genus 0.
no. Yeah, I mean, so this is really like kind of collecting bits, and the bits have marginal overlap, but they kind of create a coherent picture. But to prove something here, it's difficult.
So if I
But so the statement about the topological recursion really is kind of a statement about, studying the quiver generating series. So then, if you think about the quiver generating series, then you can construct, or you can consider quivers for which the topological recursion is feasible. I mean, you can do it, and then in that cases we have checked that topological recursion agrees with this, with the full series, so to say.
How do you derive A? Sorry.
Yeah. Well, so essentially like this. So, so if this annihilates the wave function, then you can define a function y, which is the ratio of this, which is like a kind of derivative, q derivative, and then classical limit of this a obeys the following equation with this function. It's just some transformations, nothing. And the other way of thinking about this is that you just look at this polynomial and take classical limit. So this becomes variables. I can. Do I have an example of A? Not really.
So just to make sure, so the nodes of the quiver for this lattice path story are the points in the triangle, inside the triangle.
No, there is no geometric relation. Like if you think about the like there is no geometric relation between these two pictures.
I'm not asking about this picture. I'm asking about like.
Yes. So you draw a knot and then you will have a number of crossings and you put vertices at the crossings. Okay.
Any more questions? If not, let's thank the speaker once again.